Hello again. In this lecture, we are going to discuss the exponential distribution and its main characteristics. For starters, we define the exponential distribution with the abbreviation exp, followed by a scale parameter, lambda. We read the following statement as, variable x follows an exponential distribution with a scale of a half. All right. Variables which most closely follow an exponential distribution are ones with a probability that initially decreases before eventually plateauing. One such example is the number of views for a YouTube vlog. There is a great interest upon release, so it starts off with many views in the first day or two. After most subscribers have had the chance to see the video, the view counter slows down. Even though the aggregate amount of views keeps increasing, the number of new ones diminishes daily. As time goes on, the video either becomes outdated or the author produces new content, so viewership focus shifts away. Therefore, it is more likely for a random viewing to have occurred close to the video's initial release than in any of the following periods. Graphically, the PDF of such a function would start off very high and sharply decrease within the first few time frames. The curve somewhat resembles a boomerang, with each handle lining up with the X and Y axis. All right, we know what the PDF would look like, but what about the CDF? In a weird way, the CDF would also resemble a boomerang. However, this one is shifted 90 degrees to the right. As you know, the cumulative distribution eventually approaches 1, so that would be the value where it plateaus. To define an exponential distribution, we require a rate parameter, denoted by the Greek letter lambda. This parameter determines how fast the CDF curve reaches the point of plateauing and how spread out the graph is. All right, let's talk about the expected value and the variance. The expected value for an exponential distribution is equal to 1 over the rate parameter lambda, whilst the variance is 1 over lambda squared. In data analysis, we end up using exponential distributions quite often. However, unlike the normal or chi-squared distributions, we do not have a table of known variables for it. That is why sometimes we prefer to transform it. Generally, we can take the natural logarithm of every set of an exponential distribution and get a normal distribution. In statistics, we can use this new transform data to run linear regressions. This is one of the most common transformations I've had to perform. Before we move on, we need to introduce an extremely important type of distribution that is often used in mathematical modeling. We're going to focus on the logistic distribution and its main characteristics in the next video. Thanks for watching.